Greetings of the day to all of you. My dear students, I welcome you all to another lecture in a series of lectures on space vector pulse width modulation technique, SVPWM technique. If you remember, in our last lecture, I tried to develop the concept of space vector, and we found that in a three-phase, two-level voltage source inverter, what we are doing, that the pole voltages or phase voltages or line voltages, which are basically three-phase quantities, we transform them into an equivalent two-phase reference frame, which is also called alpha beta reference frame. And then we identified that there are 8 switching states of our two-level inverter, and those 8 switching states were mapped on this alpha beta plane. For example, the first switching state is this. Let me first of all reproduce that diagram. This is voltage vector V1 and switching state is plus minus minus. Let me complete the diagram and then I will try to explain it again. So already discussed in previous class. So let us recap what we have learned in that class. So this is V3 minus plus minus RY, and this is B. This is V5 minus minus plus. So here phase R is at maximum positive, so I have put plus at phase R. Here phase Y is at its maximum positive, so plus is in the middle. And this is Y phase. Here phase Y is at its maximum positive. I have put plus here. So just 180 degree phase, 180 degree out of phase quantities are, if this is here R phase is at its maximum, here R phase will be at its minimum. So it will be minus plus plus. Here Y phase is at maximum. Here Y phase will be at negative maximum. Plus minus plus. So Y phase is at negative maximum. Here Y phase is at positive maximum. Here B phase is at positive maximum, and here B phase will be at negative maximum. Plus plus minus. So this is V1, this is V2, this is V3. I have already noted it. V4, V5, and this is V6. And then V0 switching state is minus minus minus, which is the origin, which represents the origin. It does not have any length because we know that the zero switching state results in shorting of the load, and there is no transfer of energy between source and load. So it is minus. It's called zero vector or zero switching state. Another zero vector or zero switching state is plus plus plus, where all the top devices are on and your load is again shorted through top devices, and there is no transfer of energy between source and load. And this is also called zero switching state, or V7 is called zero voltage vector. How did we get these voltage vectors? If you remember, in alpha beta plane, for example, this is our alpha plane and this is beta. I tried to first of all calculate the magnitude or amplitude of V1 voltage vector. Okay, so if you remember this V alpha, for that I found the alpha component of voltage, and I found the beta component of voltage, because this plus minus minus means that phase R is at its maximum positive and Y and B phases are having negative voltage. And in a three-phase six-step voltage source inverter, it means that phase voltage VRN is 2 by 3 VDC, and V by N and VBN are minus 1 by 3 VDC each. Okay. So this three-phase quantity we transformed into two-phase quantity, and we calculated V alpha as, if you remember, it was given by this relationship, 1 by 2 times VRO minus VYO minus VBO. And if you remember, this was equal to VDC, and it is beta component of this voltage. It was given by root 3 by 2 times VYO minus VBO. And we found that in the previous class that is equal to 0. So therefore, the net or resultant voltage vector V1, we call that voltage vector V1, that is under root of V alpha square plus V beta square. Since V alpha square is VDC, so it's under root of VDC square plus 0. That is equal to VDC itself. So that means this voltage vector plus minus minus, which actually represents a three-phase voltage, where phase R voltage is maximum and phase Y and B voltages are negative. This is maximum positive and these are negative. It is in alpha beta plane, it is represented by a voltage vector V1 whose magnitude is equal to VDC. Okay. And we also found that this voltage vector, it basically represents something like this. If you remember, let me draw the diagram again. I will draw it slightly down here. If I assume that my phase voltages are to be sinusoidal, then my phase voltages are like this. This is phase voltage VRN, for example. It should be sinusoidal. Right now, in 6-step voltage source inverter, it is not sinusoidal, but our aim is to make it vary sinusoidally using the space vector pulse width modulation technique. This is phase voltage VYN, and this is phase voltage VBN. Now this voltage vector V1, whose length is equal to VDC, which basically represents, in alpha beta plane, it is equal to VDC, its length is equal to VDC. Basically, it represents, in alpha beta plane, it represents some voltage along alpha axis and some voltage along beta axis. And in RYB plane, that is three-phase, stationary reference frame, it represents three-phase voltages, say VRN, VYN, and VBN. Now here VRN is maximum positive, so here VRN is maximum positive, whereas VYN and VBN are negative. So this voltage vector V1 is somewhere here. So this is my voltage vector V1, and it is plus minus minus. Plus minus minus means phase voltage VRN is at maximum, maximum positive of course, and whereas VYN and VBN are some negative value. Then this voltage switching state is there for 60 degrees. Okay. After a period of 60 degrees, let us take this switching state. Okay. This switching state resulted in a voltage vector of length VDC along alpha axis. Okay. Because its beta component is 0, and in terms of three-phase quantities, it represents voltages like this: VRN maximum positive, VYN and VBN negative. They are instantaneous values. Let us take second switching state, plus plus minus. We have done it already in the previous class. In the second switching state, we again find alpha component. Let me quickly give you that alpha component. We are not going to calculate it again. We have done it already in previous class. And in this switching state, V alpha that was calculated by us was found to be VDC by 2. And V beta was found to be equal to root 3 by 2 VDC. So this is my alpha component, V alpha, which is equal to VDC by 2, and my V beta is here, V beta equal to root 3 by 2 VDC. Now I want to find the resultant component. How to find the resultant voltage vector? The resultant voltage vector is the vector sum of V alpha and V beta. So let me call that voltage vector as V2. That is under root of V alpha square plus V beta square. And if you add them up, this also again comes out to be VDC. And where will that resultant vector be? So find the resultant of V alpha and V beta. That would be somewhere here. So this will be my V2. So therefore, you can see this total angle is 90 degrees, and that means voltage vector V2, whose resultant is basically V alpha plus JV beta, or under root of V alpha square plus V beta square. It lies along this axis, and that is why I am showing this vector here after an alpha of 60 degrees. So ये after 60 degrees यहाँ पे appear होता है. So what does that mean? It's very interesting. That means that first of all, inverter produces a voltage vector V1 in alpha beta plane whose length is VDC, which actually represents three-phase voltages whose instantaneous values are like this, plus, minus, minus. That is, VRN is maximum positive, VYN and VBN are some negative value. And then it retains this voltage for a period of 60 degrees. Okay, so that means यहाँ से यहाँ तक, see, this is 30 plus 30, 60 degree, it will retain this value. So let me take VRN voltage. So this VRN voltage, it is basically 2 by 3 VDC. It will retain it over a period of 60 degrees. And then when inverter applies switching state plus plus minus, it applies switching state plus plus minus. At that time, the voltage vector V2 gets applied, and this V2 is length V, it's also equal to VDC. And it gets applied across the load after 60 degrees, because we have just now found that this V2 with respect to this axis, it's at 60 degree. That means this V1 voltage vector gets applied across the load for a period of 60 degrees. And after 60 degrees, V2 voltage vector gets applied across the load. And when V2 voltage vector gets applied across the load, this vector is gone. This does not get applied across the load. This was there for 60 degrees. After 60 degrees, the new voltage vector V2, whose length is also equal to VDC, it gets applied across the load. So this V2 is equal to VDC, it is in alpha beta plane. In terms of three-phase quantities, it also represents a three-phase voltage whose R phase is some maximum value, Y phase is R phase is some positive value, Y phase voltage is also having positive value, but B phase is having maximum negative. So that you can see, that's here. So here you can see R phase is having some positive value, Y phase is also having some positive value, but B phase is having maximum negative value. So this represents voltage vector V2 with switching state plus plus minus. So that means the previous switching state was retained for a period of 60 degrees and VRN was V maximum for a period of 60 degrees. After 60 degrees, new voltage vector got applied across the load, and that impressed the voltage plus plus minus across the load, that is VRN equal to say 1 by 3 VDC, VY1 also equal to 1 by 3 VDC, but VBN equal to minus 2 by 3 VDC. So what will happen to VRN? VRN will go down, and this is now new VRN, and this VRN will get applied across the load for further 60 degrees. 60 degrees tak apply ho jayega across the load. I am not drawing VYN and VBN. I am drawing only VRN, okay, because I don't have space here. Now, when switching state minus plus minus, this third switching state, inverter now, when it applies switching state minus plus minus, okay, this switching state minus plus minus will give, alpha component equal to minus VDC by 2, and it will give beta component equal to root 3 by 2 VDC. So its alpha component is not along this, it is negative. This is V alpha, it is negative, it is minus VDC by 2. Whereas beta component is this, is root 3 by 2 VDC. So how do you find its resultant? So its resultant is voltage vector V3, which is again equal to V alpha square plus V beta square. So it's phasor sum of V alpha and V beta, and it is somewhere here. Okay. This is my V3, and this V3 comes out to be again equal to VDC. So this is my V3. This was my V2, this is V3, and it is also equal to VDC. That means after 60 degree interval, my voltage space vector, new voltage space vector gets applied across the load. And what is the new voltage space vector? V3. So first V1 voltage vector got applied across the load. Then after 60 degrees, V2 voltage vector got applied across the load. Then after another 60 degrees, this is again 60 degree interval with respect to this, and total 60 plus 60, 120 degree, V3 voltage vector got applied across the load. And this V3 voltage vector means that R phase is having some positive value. We can see R phase is having some positive value. Say earlier it was having a value of 2 by 3 VDC, now 1 by 3 VDC, and it will be there for 60 degrees. So you can continue like that. Then for next switching state is minus plus plus. for this minus plus plus, if you find V alpha, we have already found it, I am not repeating that, you can go back to your notes. V alpha is equal to minus VDC and V beta is equal to 0. So therefore, this is my V alpha equal to minus VDC along this axis. It does not have V beta is 0. It's along this axis. So therefore, this voltage vector V4 is also equal to VDC, because total voltage, resultant voltage is again under root of V alpha square plus V beta square. It is equal to VDC, but it is along this axis, and this angle is again 60 degrees. That means after 60 degrees, a new voltage vector gets applied across the load, whose switching state is minus plus plus. Minus plus plus means R phase is having some maximum negative value now. R phase is having maximum, where was I? Yeah, here R phase is having negative value. Let me first complete this. R phase is having negative value. ये देखिए R phase negative value है, it will go down, and for 60 degrees it will retain this negative value. And then when new voltage vector V4 gets applied across the load, R phase is having maximum negative value. ये देखिए आप, R phase अब maximum negative value है. So it will go here and it will retain this maximum negative value for 60 degrees. Then next switching state is this. आपकी नई switching state है V5, ये minus minus plus. इसमें भी अगर आप V alpha निकालेंगे, it will be some negative quantity, and V beta will be also be some negative quantity. That means यह आपका V alpha है, यह आपका V beta है, and where will be a resultant voltage vector V5? That will be vectors phasor sum of the two. So this will be V5, and that V5 will also be equal to VDC. We have seen that yesterday. So after 60 degrees, my next new voltage vector is V5. So this is equal to, its length is also equal to VDC, and it represents three phase voltages whose status is minus minus plus. That means R phase voltage is some negative value, Y is also some negative value, and B phase is maximum positive. So it is this. Here you can see R phase is having some negative value, Y phase is also having some negative value, but B phase is having maximum positive value. So this was my voltage vector V3. V3 was minus plus minus. This was my voltage vector V4. V4 was minus plus plus, and this will be my voltage vector V5. V5 will be minus minus plus, and V5 means R phase is having some negative value. So it will come down a negative value for next 60 degrees rahega. It will retain that negative value. After that, we have last switching state. Last switching state in the cycle is plus minus plus. So when you find this, apply this plus minus plus switching state across the load, it will give V alpha equal to minus VDC by 2, and it will give V beta equal to root 3 by 2 VDC. That means here alpha negative degi, minus VDC by 2 is V alpha, and V beta is V beta is, I'm sorry, V alpha will be positive now. V alpha will be, V alpha will be positive, it will be VDC by 2, and V beta will be some negative value, okay? It will be minus root 3 by 2 VDC. So ये ऐसे होगा, V alpha equal to VDC by 2 and V beta minus root 3 by 2 VDC. Resultant vector यहाँ होगा, and that is this. That gives voltage vector V6, which is also equal to, whose length is also equal to VDC, right? So that means after 60 degrees, a new voltage vector V6 equal to VDC will get applied across the load, which represents the three phase voltages, in which the status of three phase voltages is like this. VRN is some positive value, VYN is maximum negative, and VBN is also positive. यहाँ आप देख सकते हैं, VYN is maximum negative, VRN and VBN are positive. So therefore go up, or VRN positive रहेगा. So therefore previously also it will be something like this. So this completes my VRN phase voltage, and you can see it is a 6-step voltage. So therefore, when inverter is operated, initially voltage vector V1 equal to VDC gets applied across the load, which represents phase R voltage equal to VRN. Let me draw all the three these phase voltages for better clarity. This is just a recap of what we have already learned in previous class. Let me draw VRN. So this is VRN, VYN, phase voltage VYN will start after 120 degrees. This is 60 plus 60, 120 degrees. यहाँ से शुरू हो जाएगी, and these are various 60-degree interval points. Will start from here. Okay, come down. This is V by N, and my VBN will start after another 120 degrees. 60 plus 60, 120 degrees. यहाँ से शुरू हो जाएगी. So 60 plus, so it will start from here. Okay, so these are my three voltages. Now you can start from here. When voltage vector, when inverter is operated, it applies in alpha beta plane. It applies a voltage vector V1 equal to VDC across the load. And when you transform that from alpha beta reference frame to ABC reference frame, three-phase reference frame, stationary reference frame, that represents three phase voltages, VRN, VYN, and VBN. VRN will be maximum positive, VYN and VBN will be negative. So that is this instant. VRN is maximum positive, VYN is negative, VBN is negative. For example, VRN is 2 by 3 VDC, VYN and VBN are minus 1 by 3 VDC each. So therefore this represents the voltage vector V1, whose status is plus minus minus. And after 60 degrees, what happens? It applies next voltage vector. So this voltage vector is now gone. After 60 degrees, it does not apply this voltage vector. It applies this voltage vector V2, whose length is also VDC, and when you transform it from alpha beta reference frame to ABC reference frame, it represents the three phase voltages VRN, VYN, and VBN. VRN is positive, VBN is positive, and VRN is positive, VYN is positive, VBN is maximum negative. So that means for 60 degrees, it will retain this voltage, and after 60 degrees, VRN is positive. So it is positive 1 by 3 VDC. VYN is also positive 1 by 3 VDC. But VBN is maximum negative. You can see VBN is maximum negative. It is minus 2 by 3 VDC. Okay. So applies this voltage vector after 60 degrees. 60 degrees के बाद, after 60 degrees, it applies new voltage vector. And that is V2 equal to plus plus minus. And this voltage vector gets applied across the load for 60 degree interval. You can see this is 60 degree interval. So now load voltage is, VRN plus 1 by 3 VDC, VYN is plus 1 by 3 VDC, and VBN is minus 2 by 3 VDC. After another 60 degrees, a new voltage vector will get applied across the load, V3 equal to VDC, and it applies three-phase voltages like this. VRN will be negative. You can see VRN is now negative. VBN will be most positive, maximum positive. VBN is maximum positive. VYN is maximum positive, and VBN is also negative. So VRN is negative, VYN is maximum positive, VBN is negative. So this is my voltage vector V3 minus plus minus. It gets applied across the load for 60 degree interval. So now load voltage का status ये है, three phase voltage which gets applied across the load, and it remains there for 60 degree interval. Because after 60 degree interval, you can see when this switching state is applied, you get this, the voltage vector यहाँ से यहाँ आ जाता है. previously ये voltage vector, this voltage vector was getting across the load, and after 60 degrees new voltage vector will get applied across the load. So after another 60 degrees, voltage vector V4 equal to VDC will get applied across the load, in which R phase voltage is maximum negative. You can see R phase voltage is maximum negative. Y and B phases are positive. So this is new voltage vector V4 with status switching state minus plus plus, which gets applied across the load. And this is the three-phase voltages which will get applied across the load for this 60-degree interval. And when inverter applies this switching state, okay, when inverter switching state is this, it applies new voltage vector. This voltage vector is not applied now across the load. It applies new voltage vector V5 equal to VDC, but after 60 degrees. That means this voltage vector gets applied across the load for 60-degree interval. You can see. And after 60-degree interval, new voltage vector V5 gets applied across the load, whose length is again VDC, and which gives phase voltages VRN negative. You can see VRN is negative. VYN is also negative. VYN is negative. While VBN is maximum positive. Okay. So this voltage vector will be there for another 60 degrees. So V5 minus minus plus. Then this switching state will give us new voltage vector after 60 degrees. That means this voltage vector will get applied across the load after 60 degrees. 60 degree तक यही voltage vector था across the load. 60 degree तक यही voltage vector था across the load. After 60 degrees, new voltage vector V6 will get applied across the load, which gives phase or voltage VRN positive. You can see VRN is positive. VYN is maximum negative. You can see VYN is maximum negative, and VBN is also positive. So this is switching state or voltage vector V6 plus minus plus, and it remains there for 60-degree interval. After 60 degrees, so this completes our one cycle. 60 plus 60 plus 60 plus 60 plus 60 plus 60, that is 360 degrees. That means one cycle of voltage will get applied across the load. And when I say one cycle of voltage, three-phase voltage gets applied across the load. It's like this. Phase voltage VRN, phase voltage VYN, and phase voltage VBN. 6-step voltage which gets applied across the load. Right? So therefore, in the nutshell, we could say that in 6-step mode, the inverter applies voltage vector V1 across the load. This voltage vector is there for 60 degrees. After 60 degrees, it applies voltage vector V2 across the load. After another 60 degrees, it applies voltage vector V3 across the load. After another 60 degrees, it applies voltage vector V4 across the load. After another 60 degrees, it applies voltage vector V5 across the load. And after another 60 degrees, it applies voltage vector V6 across the load, and then cycle is complete. And these voltage vectors which get applied across the load after every 60-degree interval in three-phase reference frame, they represent three-phase 6-step voltage waveforms like this. Is that clear? Now, our aim is that we don't want this type of voltage across the load. What type of voltage we want across the load? We want sinusoidal voltage across the load. I want my VRN should not be 6-step voltage. It should be sinusoidal voltage like this. This should be my VRN. VYN should also be sinusoidally varying across the load. This should be my VYN. And VBN should also be sinusoidal voltage getting applied across the load. A set of three-phase sinusoidal voltages should get applied across the load. Right now, when these 6 voltage vectors are applied across the load after every 60-degree intervals, they apply, this is voltage vector V1, it is there for 60 degrees. This is voltage vector V2, it is there for 60 degrees. Voltage vector V3, it is there for 60 degrees. Voltage vector V4, this is there for 60 degrees. This is V5, and similarly, this is somewhere here V6. These voltage vectors there. And these voltage vectors, they represent, 6-step voltages. They are not sinusoidal voltages, because this V1 is there for 60-degree interval, and it represents 6-step voltages across the load. Similarly, V2, V3. Now, I don't want my voltage to be 6-step voltages like this. I don't want, this voltage there for 60 degrees, this voltage there for 60. I want continuously varying voltage, like sinusoidally varying voltage like this. For example, my VRN is actually like this by application of these voltage vectors. But I want sinusoidally varying voltage, this type of voltage to get applied across the load. Is that possible? Answer to this question is yes, that is possible. That is possible if instead of applying these 6 voltage vectors after every 60 degree interval, I produce a reference voltage vector which is, rotating in the counterclockwise direction continuously at a speed given by the frequency of the voltage, say 50 hertz, maybe 50 hertz or 60 hertz supply. So instead of applying voltage vector V1 for 60 degrees and then voltage vector V2 for 60 degrees, and then V3 and so on, these voltage vectors for 60 degree each, if I am able to produce a reference voltage vector Vref, which is not applied across the load after every 60 degree interval, which is continuously rotating like this, and it is traveling in a circular path like this. It is like this. It's moving along this circle. It's rotating. It's a rotating reference vector like this. If I am able to generate this rotating reference vector, this rotating reference vector will represent a set of 3-phase sinusoidal voltages applied across the load. Our VRN, VYN and VBN, they will become sinusoidal. For 6-step inverter operation, V1 was applied and it was there for 60 degrees. After 60 degrees, V1 was gone, V2 was applied across the load for 60 degrees. After 60 degrees, V3 was applied across the load. After another 60 degrees, V4 was applied across the load, and this remained there for 60 degrees. After another 60 degrees, V5 was applied across the load. It was there for 60 degrees, and after another 60 degrees, V6 voltage vector was applied across the load, and that completed cycle, and that gave us 6-step 3-phase voltages, VRN, VYN, VBN. In order to get sinusoidal voltages, not 6-step voltages, instead of applying these voltage vectors discretely after every 60 degree interval, if I am able to generate a reference voltage vector and move it continuously along this circle, a rotating or revolving voltage vector, that revolving voltage vector in alpha beta reference frame will represent some V alpha and V beta, and in ABC reference frame that will represent some voltages, say VRN, VYN, VBN, say phase voltages, similarly line voltages, and those voltages will be sinusoidally varying like this. So that means this rotating reference vector, which is rotating continuously in counterclockwise direction in a circular path, it represents 3-phase set of sinusoidal voltages or 3-phase set of sinusoidal currents. Since our voltage source inverter gives voltage as its output, so it will represent 3-phase sinusoidal voltages like 3-phase voltages VRN, VYN and VBN, which are sinusoidally, varying like this. Or if you say line voltages VRY, VYB and VBR, it represents those 3-phase line voltages which are also sinusoidally, sinusoidal like this. Now the question is how to generate this rotating reference frame. Now this rotating reference frame is analogous to your revolving magnetic field in 3-phase induction motor, because in 3-phase induction motor, if you remember, we had 3, this was phase R, phase Y and phase B, or in alpha beta reference frame, this was alpha axis, beta axis. And in these 3-phase, there was 3-phase voltage or 3-phase current, sinusoidal currents were flowing, or in alpha beta reference frame, sinusoidal currents which are 90 degrees apart with respect to each other, they were flowing in this, and both the reference frames were producing a rotating magnetic field like this. So this rotating magnetic field was produced because of these sinusoidal currents. Similarly, if in voltage source inverter, using space vector concept, we are able to produce a rotating reference vector like this. We know that this rotating magnetic field revolves in a circular path. It revolves, like this. It's a revolving magnetic field in three-phase induction motors. In case of inverters using space vector concept, if I am able to produce a rotating vector, reference vector like this, which is analogous to rotating magnetic field, this rotating vector will represent three-phase sinusoidal voltages. It will be representative of three-phase sinusoidal voltages. Okay? So the question is how to generate this rotating reference vector. This rotating reference vector may be somewhere here. Say, for example, these are my voltage vectors, V1, V2, V3, V4, V5 and V6, whose positions are already, after every 60 degrees given. From these voltage vectors, I can get a reference vector, Vref, which is at an angle of alpha with respect to this alpha axis. This is alpha axis and this is my beta axis. And this rotating reference vector will be rotating continuously in a circular path, and it will generate sinusoidal voltages, not 6-step voltages. The question is how to generate this reference vector. Before I discuss with you this reference vector concept, let me tell you that this space vector diagram, this is called space vector diagram. This space vector diagram can be divided into 6 triangles. For example, if I join these tips together, this tip with this tip, if I join the tips of these vectors together like this, so I get 6 triangles. This is one triangle, this is another triangle, this is another triangle, another triangle, another triangle, and so I get 6 triangles. In these 6 triangles are called sectors. For example, this is called sector 1. This is called sector 2, second sector. This is called sector 3. This is sector 4. This is sector 5. And this is sector 6. So these 6 triangles, enclosed triangles, they are called sectors, and this gives a regular hexagon. You can see this. If I join the tips of these voltage vectors, it gives me a hexagon. This is a hexagon, and this hexagon will have 6 triangles, and each triangle is called a sector. This is sector 1, sector 2, sector 3, sector 4, sector 5, sector 6. Sector 1 is made up of 2 voltage vectors, V1 and V2, which are representing the switching states plus minus minus and plus plus minus. Sector 2 is made up of 2 voltage vectors, V2 and V3. Sector 3 is made of voltage vectors, V3 and V4. Sector 4 is made of voltage vectors, V4 and V5. Sector 5 is made of voltage vectors, V5, V6, and Sector 6 is made of voltage vectors, V6 and V1. And in addition to these vectors, these 0 voltage vectors also, V0 and V7. Now let us take sector 1. Let me take sector 1. And let us see how we can generate a rotating reference vector in sector 1. So this is my sector 1. Sector 1 comprises of voltage vector V1. This is my voltage vector V1, right? Which is equal to VDC. And it represents the switching state plus minus minus. And this comprises of another voltage vector V2. This is my voltage vector V2 at an angle of 60 degrees. Its length is also equal to VDC in alpha beta plane, and it represents the switching state plus plus minus. It is plus plus minus. And then it will have 0 voltage vector also. 0 voltage vector will be either V0, which is minus minus minus, or V7 plus 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 at the origin. These 0 voltage vectors will not have any length, because when these voltage vectors are applied, the line voltages are 0. The line load voltages are 0. So that's why they are called 0 voltage vectors. They short the loads. Okay. Now, I want to create a reference vector, V reference. This is my V reference. a rotating reference vector, which is rotating, along a circular path in the counterclockwise direction, and which basically represents a set of three-phase sinusoidal voltages. How can I generate a rotating reference vector? Say in sector 1, I can generate it, say, if I draw a line parallel to this V2 vector. So this is the line parallel to V2 vector. So this is vector V1. So therefore, I can generate this reference vector if I apply voltage vector V1 for a time of T1 by Ts, and then this is V2, a parallel line AB V2. If I apply voltage vector V2 for a time interval T2 by Ts, where what is this Ts? Ts is called subcycle. Subcycle means if in a triangle comparison type PWM method, we have a cycle, and each cycle is divided into two half, this is carrier cycle, half carrier cycle, this is Ts, this is Ts. So this half carrier period is called subcycle, this is also called subcycle. Similarly, in space vector PWM, this Ts is subcycle. Analogously, for triangle comparison time PWM method, it is half of the carrier period, subcycle. So let's come back to here. I can produce this reference vector, and I can make it to be somewhere here at an angle of alpha if I apply voltage vector V1 for a period of T1 out of Ts, subcycle, in a subcycle of Ts. And then I apply voltage vector V2 for a period of T2 by Ts. And not only these, then if I add this T1 and T2, T1 plus T2, see this T1 plus T2 should be equal to Ts, because what is the total time period for which these vectors are applied? V1 is applied for a period of T1, V2 is applied for a period of T2. So T1 in a subcycle of Ts, that's in the time period of Ts. So T1 plus T2 should be equal to Ts. But when you add T1 plus T2, it always comes out to be less than Ts. So therefore, there is inequality. So therefore, T1 plus T2 plus something else should be here, which will make it equal to Ts. So what will we add to T1 and T2? We will add zero voltage vectors, zero timings. So then what I will write? I will write T1 plus T2 plus Tz. That is equal to Ts. Where T1 is the time period for which voltage vector V1 is applied across the load. T2 is the time period for which voltage vector V2 is applied across the load, and Tz is the time period for which voltage vector V0 or V7 is applied across the load. Now this T1 plus T2 plus Tz always comes out to be equal to Ts, so इसमें ये equation satisfy हो जाती है. So you have to necessarily add this Tz. That means you don't have to apply only V1 or V2. For some period you have to apply, out of these two zero voltage vectors, you have to apply zero voltage vector also for some time, so that this equation is satisfied. T1 plus T2 plus Tz is equal to Ts. Now applying this zero voltage vector is not going to change inverter output voltage. It will remain sinusoidal, because zero voltage vector means whenever zero voltage vector is applied across the load, it means load voltage during that interval is zero. So it is not going to affect the shape of the voltage waveform, right? So therefore, I can use volt-second balance. I can write, so Vref, this reference vector, is there for a period of Ts, where Ts is the subcycle time interval. So this is equal to, this is volts into time, volt second. This is equal to V1 into T1, because voltage vector V1, this, which is switching state plus minus, it's applied for a time period of T1, plus voltage vector V2 is applied for a time period of T2. So V2 into T2 plus zero voltage vector Vz is applied for a time period of Tz. Okay. So this satisfies the volt-second balance. So Vref into Ts is equal to V1 T1 plus V2 T2 plus Vz Tz. Right? Where total subcycle interval is equal to T1 plus T2 plus Tz. Okay? Or Tz, that is time period for which zero voltage vector is applied. It is total subcycle interval minus T1 minus T2. Okay, this is it. So from this, if you want to find Vref, our aim is to find this Vref, equation for Vref. So this Vref will be equal to V1 T1 by Ts, because this Ts will divide here in each term, plus V2 T2 by Ts plus Vz Tz by Ts. As far as voltage vector V1 is concerned, this voltage vector V1, what is this? This is VDC at an angle of 0 degree. It's along alpha axis, so it is VDC at an angle of 0 degree. And what about voltage vector V2? V2 is applied, it's also equal to VDC, but it is at an angle of 60 degree, because we know that V2 gets applied across the load after 60 degree interval. So it is VDC at an angle of 60 degrees. So you can find it will be VDC cos 0 plus VDC sin 0. Similarly, this will be VDC cos 60 degrees plus JVDC sin 60 degrees. If you substitute and put this V1, V2 value in this equation and simplify, you will get finally this expression. You will get the expressions for dwell times. So dwell times means times for which different voltage vectors are getting applied across the load. Dwell times means time T1. You will find it. I am not going for that derivation. You can find those derivations in all the books. So I will give you expression for dwell times T1, T2 and Tz. So this T1 will be equal to Vref into sine of 60 degrees minus alpha degrees divided by VDC into sine 60 degrees into total subcycle interval T1, Ts. So this is dwell time T1. This is a time period for which voltage vector V1 has to be applied across the load. Now what about T2? T2 will be equal to Vref into sine alpha divided by VDC into sine 60 degree into Ts. This is T2. And what about Tz? Tz is simply Ts minus T1 minus T2. You know what is total subcycle interval. That depends upon the switching frequency. If switching frequency is 10 kHz, you can find this Ts. And then minus T1 you can find from this equation, T2 you can find from this equation. Substitute here, you will get the time interval for which zero voltage vector has to be applied across the load. Now it is very interesting, these are very interesting equations. For example, when your reference vector is along alpha axis here, along alpha axis only V1 voltage vector is applied across the load. Because along alpha axis, what is alpha equal to? Alpha is equal to 0. So this is sine 60 degree divided by sine 60 degree. So ये cancel हो जाएगा. So T1 is equal to Vref by VDC Ts. So T1 is applied. Say when your voltage vector V1 is along, when your reference vector Vref is along alpha axis, which voltage vector is applied? VDC is applied, V1 is applied, because alpha is equal to 0, so it is applied for this much of period. Is V2 applied here at that time? V2 is not applied, because since alpha is equal to 0, here alpha is equal to 0, sine 0 in the second equation is 0, so T2 is 0. T2 represents the time for which V2 voltage vector is applied. So V2 is not applied when your reference vector is along this axis, right? Then, suppose your reference vector is now somewhere here. How did you bring your reference vector from this position to this position? It was possible only by applying both the voltage vectors. Applying voltage vector V1 for time interval T1 and applying voltage vector V2 for time interval T2. Now we can see when alpha increases, that means here alpha was 0. Now alpha increases means your reference vector is now rotating. Let us say it is somewhere here. Now alpha is some value, say 10 degrees or 15 degrees. So therefore the time interval for which V1 voltage vector is getting applied across the load is T1. It is Vref sine of 60 minus that 15 degrees divided by this. and T2 will V2 will also get applied now, because T2 is V ref sine alpha. Alpha is not now 0. Alpha is maybe 10, 15 or 20 degrees. So sine 15 degrees or sine 20 degrees divided by this into Ts. So that means for some period T2 will get also applied. So when both voltage vectors are getting applied, V1 is getting applied for a time interval T1, V2 is getting applied for a time interval T2, your reference vector will not be here. It will be somewhere in between V1 and V2, somewhere here. And as it moves like this, alpha increases. And as alpha increases, you can see T1 decreases. You can very clearly see as alpha increases, say, in this equation. जैसे alpha increase होता है, that means as you want to rotate your reference vector, you want to move it in this direction, you are increasing alpha. ये alpha increase हो रहा है. When alpha increases, obviously sine of 60 degree minus alpha decreases, so T1 decreases. And in this equation, when alpha increases, sine alpha also increases, so T2 also increases. So that means earlier your reference vector was here, alpha was 0. Now you want your reference vector somewhere here, so alpha is now increasing. When alpha is increasing, the time for which V1 vector is applied, it slightly decreases, and the time for which V2 vector applies, V2 vector also gets applied for some time. And your reference vector is, say, somewhere here. Now if you want your reference vectors to move from this position to this position, so alpha increases, and as alpha increases, the time interval for which V1 vector is getting applied across the load, that decreases, and the time interval for which V2 vector gets applied across the load, that increases. So that pulls the vector towards V2 vector. So ये आपका reference vector यहाँ आ जाता है. So it moves, and when reference vector reach this stage, इस stage पे alpha कितना है? 60 degrees. So T1 कितना है? Sine 60 minus 60, 0. So no V1 vector gets applied across the load at that time. Only V2 vector gets applied across the load. So when reference vector is along alpha axis, at that time only T1 is there. V1 vector only gets applied across the load. V2 vector doesn't get applied across the load. And when your reference vector is along V2 vector, here alpha is 60 degrees, so T1 is 0, T2 is maximum. That means at that time only V2 voltage vector gets applied across the load. V1 space vector does not get applied across the load. And in between, both the vectors are getting applied across the load. And as your reference vector rotates, as it rotates like this, alpha increases, so that time interval for which V1 gets applied across the load, that decreases, and the time interval for which V2 vector gets applied across the load, that increases. So in very simple terms, I can explain it like this. Again, I will take V1 voltage vector, which is equal to VDC, which represents plus minus minus switching state, and this is V2 voltage vector, which is also equal to VDC, which represents the switching state plus plus minus. This is another voltage space vector. Let us suppose, and I have 0 voltage vector also, minus minus minus. I have another 0 voltage vector, plus plus plus. Let us suppose my reference vector is here, Vref. When my reference vector is along V1 voltage space vector along alpha axis, T1 is maximum and T2 is equal to 0. That means only V1 voltage space vector gets applied across the load, and your reference vector is along V1 axis. Fine. Now I want my reference voltage vector to be somewhere here. Let me trace this circular path. I want it to move to this position. If I want to move it to this position, this angle alpha, which was previously 0, it is now maybe some 5 degrees or 10 degrees. So when alpha increases, now both the voltage vectors will get applied across the load. Earlier only V1 voltage vector was getting applied across the load. Now V1 will get applied across the load for a time interval T1. V1 will get applied for a time interval T1, and V2 will get applied for a time interval T2. And since alpha is now some positive value, say 5 degrees or 10 degrees, V1 will get applied across the load for a longer period, and V2 get applied across the load for a smaller period. अब V1 ज़्यादा पीरियड के लिए अप्लाई है, V2 कम पीरियड के लिए है. Say time interval T1 is 90% of total. Say T1 is 0.9 TS and T2 is only 0.1 TS. So that means time interval for which voltage space vector V1 is applied across the load, it is 90% of total subcycle period. And time interval for which voltage vector space vector V2 is applied across the load, it's only 10% of total time. So therefore, किसका पलड़ा भारी है? V1 का पलड़ा भारी है. V1, when V1 gets applied across the load, it tries to pull your reference vector towards itself. And if V2 gets applied across the load, ये इसको अपनी तरफ pull करेगा. लेकिन ओवरऑल आप देखेंगे V1 will be very close, reference vector Vref will be very close to V1 because time interval T1 is large. After some interval of time, I want my reference vector somewhere here. So alpha is now increasing. Now when alpha is increasing, we have just now seen from the equation T1 decreases and T2 increases. So that means the time interval for which V1 space vector is applied across the load, that decreases, and the time interval for which V2 space voltage vector applies across the load, that increases. तो अब इसका इम्पैक्ट कम हो जाएगा रेफरेंस वेक्टर पे. ये रेफरेंस वेक्टर को अपनी तरफ पुल करेगा, लेकिन ये ज्यादा देर अपनी तरफ पुल करेगा. Since V1 will pull it towards itself, V2 will pull it upwards towards itself. Since T2 is more than T1, तो V2 will win over V1, तो ये इसको अपनी तरफ पुल करेगा, तो ये उस तरफ जाएगा. After another 15 or 20 degrees, my reference vector will be now somewhere here. Why it will be here? Yes, now it will move more closer towards V2 because alpha is increasing. As alpha increases, T1 decreases, T1 further decreases, and T2 further increases. That means the time interval for which V1 space voltage vector is applied across the load, that further decreases, and the time interval for which V2 space voltage vector gets applied across the load, that further increases. तो इसका मतलब V2 इसको ज्यादा अपनी तरफ पुल करेगा, तो ये उसी की तरफ जाना शुरू हो जाएगा. So it will keep on moving towards it till. So for example, यहाँ पे आप देख सकते हैं, let us suppose here alpha is 55 degrees. When alpha is 55 degrees, what is sine of 60 minus 55 degrees? That's only, because your T1, you have written that equation, T1 is equal to Vref into sine of 60 degrees minus alpha by VDC into sine 60 degrees. And T2 is Vref sine alpha by VDC into TS. VDC sine 60 degrees. When alpha is 55 degrees, what is T1? It is sine of 60 minus 55 degrees. It is only sine 5 degrees, and sine 5 degrees is very small. That means the time interval for which V1 voltage space vector is applied across the load, it is very, very small, extremely small. Whereas sine 55 degrees here is very large. That means T2 for which V2 voltage vector is applied across the load, it is extremely large. So V2 will get applied across the load for a very large period of time, and V1 gets applied across the load for a very small period of time. The net result is that your reference vector, it will be more inclined towards V2 than V1. This is how we produce a rotating reference vector. This is in sector 1. यहाँ से यहाँ तक फिर सेक्टर 2 शुरू हो जाएगा. सेक्टर 2 में वोल्टेज स्पेस वेक्टर V2 और वोल्टेज स्पेस वेक्टर V3 अप्लाई होते हैं. दिस इज माइनस प्लस माइनस. This V3 is also equal to VDC. So now what will happen in sector 2? In sector 2, V2 voltage space vector gets applied for some time, and V3 voltage space vector gets applied for some time. When your reference vector is now somewhere here, T1 for which V2 voltage space vector is applied across the load, it is very high, and T2 for which time interval T2 for which V3 voltage space vector is applied across the load, it is very, very small. So the net result is that your reference vector is very close to V2 than V3. तो थोड़ी देर के बाद अल्फा इंक्रीज हो जाएगा. As alpha increases, the T1 will decrease, T2 will increase. That is the time interval for which V2 voltage vector is applied across the load, that decreases, and time interval for which V3 voltage space vector is applied across the load, that increases. तो ये वेक्टर ज़्यादा देर के लिए लोड के अक्रॉस अप्लाई होगा, ये कम, so it will pull reference vector towards itself, and then as alpha increases, your reference vector will keep on moving towards V3 till it aligns along V3. When it aligns completely along V3, at that time T1 is 0, T2 is maximum. So therefore this rotating reference vector, it will keep on rotating in sector 2 by applying voltage vectors V2 and V3 for time intervals T1 and T2. उसके बाद sector 4 शुरू हो जाएगा. ये मेरा sector 3. In sector 3, which voltage space vectors I have? Which voltage space vectors have to get applied across the load? This is V3, this is V4. V4 means minus plus plus. So the time interval for which, for some time V3 voltage space vector will get applied across the load, and for some time V4 voltage space vector will get applied across the load. When reference vector is very close to, say it is very close to V3, T1 is very large, T2 is very small. That means the time interval for which V3 voltage space vector is applied across the load is very large, and the time interval for which V4 voltage space vector is applied across the load is very small. The result is that reference vector will be very close to V3. Like as the time progresses, alpha will keep on increasing, and as alpha increases, T1 will decrease, T2 will increase. That means V3 will get applied for less time, V4 will get applied for more time, and your reference vector will keep on moving towards V4 in a circular path till it aligns along V4 here. This is what happens in sector 3. Then we have sector 4. Sector 4 is made up of V4 voltage space vector and V5 voltage space vector. V5 voltage space vector is minus minus plus. Okay. Here also, V4 voltage space vector will get applied for time interval T1. V5 voltage space vector will get applied for time interval T2, given by same equations. Okay, this is sector 4, given by the same equations which I have already discussed with you, which I have written few moments back. It is like this. This is V5 minus minus plus. And then your reference vector will keep on rotating like this, using the same logic as we have used in other sectors. This is sector 4. Then I have 1, 2, 3, 4. Sector 5. Sector 5 is, this is sector 5. It is made up of V5 and V6 voltage vectors. V6 voltage vector is plus minus plus. Well, this may be the time interval for which V5 voltage vector is applied across the load is T1, and T2 is the time interval for which this voltage vector is applied across the load. And as alpha increases, T1 decreases, T2 increases, so your reference vector will keep on moving from V5 to V6 in a circular trajectory like this. So keep on moving like this. So that completes sector 5. And then you have sector 6, last sector. Sector 6 is made up of V6 voltage vector and V1 voltage vector. The time interval for which V6 voltage space vector is applied across the load is T1, and the time interval for which V1 voltage vector is applied across the load is T2. Initially, when your reference vector is close to V6, T1 is much higher, T2 is smaller. But as alpha increases, T1 decreases, T2 increases, so its influence increases, its influence decreases, and your reference vector gets pulled towards V1. So it moves in a circular path like this. So this completes one cycle. So this is how you actually produce a rotating reference vector. And this rotating reference vector starts rotating from here, revolves in the counterclockwise direction in a circular path and comes back. It completes one cycle, and this reference voltage vector V reference is made in each sector. It is actually created in each sector by time averaging of the corresponding voltage space vectors. For example, in sector 1, the time averaging of V1 and V2 voltage space vectors creates rotating reference vector. In sector 2, the time averaging of V2 and V3 voltage space vectors makes it rotating like this. Similarly, in other sectors. Okay, why I am saying time averaging? Because you are applying a particular voltage space vector for time interval t1 and another voltage vector for time interval t2 and zero voltage vector for time interval tz, so that your Vref is equal to V1 into T1 by Ts plus V2 into T2 by Ts plus Vz into Tz by Ts. This is time averaging. V1 voltage vector, for example, in sector 1, it's applied for a time interval T1 out of Ts. And V2 voltage vector is applied for a time interval of T2. And Vz is applied for a time interval of Tz. And as alpha increases, T1 decreases, T2 increases, then this voltage vector is applied for less time, this is applied for more time, and that pulls it, that makes it rotate in a circular path like this in this sector and then in other sectors also. This is how a revolving or rotating reference vector is produced, and in each sector this rotating reference vector is produced by time averaging of corresponding voltage space vectors V1, V2 in sector 1, in sector 2 time averaging of V2 and V3, in sector 3 time averaging of V3 and V4, then in sector 4 V4 and V5, in sector 5 V5 and V6, and in sector 6 time averaging of V6 and V1, and it creates a rotating reference vector. And let me tell you, this rotating reference vector, which is actually in alpha beta plane, it actually represents a set of three-phase sinusoidal voltages. If you draw the phase voltages now, it will generate phase voltage Vrn. It will not generate 6-step voltages like this. It will generate sinusoidal voltages because your reference vector is not here for 60 degrees and you are new after 60 degrees. This vector is not applied across. No, at each and every time in sector 1, both the voltage vectors are applied across the load, and time averaging of these voltage space vectors produces a revolving voltage vector, reference vector. Similarly, in sector 2, time averaging of V2 and V3 voltage space vectors produces a revolving reference vector Vref, and which represents a set of three-phase voltages. Say this is Vrn, this is Vyn, and this is Vbn. This is the basic concept of space vector. So our rotating reference vector, the aim is to generate a rotating reference vector, and this is how we generate this rotating reference vector. In each sector, it's generated by time averaging of corresponding voltage space vectors. Okay, so this rotating reference vector, when it completes one cycle, it basically represents a set of phase voltages, sinusoidal phase voltages, or a set of three-phase sinusoidal line voltages. Fine. Now this, as far as the sample time is concerned, sample time means, say for example, if I take sector 1, this is V1 plus minus minus, and this is voltage space vector V2, which is plus plus minus, and this is V0 minus minus minus, and this is V7 plus plus plus, zero voltage vectors. And this is circular trajectory in which I want to create a reference vector. This is Vref. I can produce Vref rotating like this. This is, say for example, this is 10 degrees, 10 degrees, 10 degrees, 10 degrees, 10 degrees, and 10 degrees. So say earlier your reference vector was along V1. After 10 degrees, it's somewhere here. After another 10 degrees, it's here. After 10 degrees, it's here. After 10 degrees, it is here. 10 degrees till it completes this sector. ये आपका sector 1 है. It rotates in this sector. So how many samples have we this? अगर आप 10-10 डिग्री का सैंपल लेंगे, 1, 2, 3, 4, 5, 5 सैंपल हमें एक सेक्टर में मिलेंगे, including this 6 sectors. So 10, 10 plus 20, 30, 40, 50, 60, क्योंकि each sector is of 60 degree interval. Now this इसी तरह second sector में, if you consider second sector, sector 2, उसमें भी you will have 10 degrees, 10, 10, 10, 10, 10, and similarly in other. Lesser the number of these are called sample time, samples. This is one sample, this is another sample. 10-10 degree के बाद आप एक sample लेते हैं. If you do it, your phase voltages will be something like this. में ripple ज़्यादा होगा. It will have more ripple. Because आप पहले ये sample, your reference vector is somewhere here. Say it is here. So it will remain there for 10 degrees. Then it moves here, goes up. It will remain there for 10 degrees. ये जो 10 degrees है, it gives more ripple. Actually, in one sector, when you rotate your reference vector from this position to this position, you should have large number of samples, not just 5 or 6 samples. It has been seen that hundreds and hundreds of samples are there in each sector, hundreds of samples. It depends upon the switching frequency. Depends upon switching frequency. Because, for example, if switching frequency is just 100 hertz, say 100 hertz, so sample time will be 1/2 into 100. ठीक है, sample time ये होता है half of the carrier. पूरा carrier ये है, this is TS, this is TS. So पूरा अगर आप लेंगे time period, that is 1/100. But this TS is half carrier period, so it is 1/2 into 100. So it is 1/200. So sample time is very, very small. On the other hand, if you take switching frequency, say 10 kilohertz, तो इसमें here sample time is very, very small. That means उसमें samples आपके दूर दूर आएंगे. You'll get only a few samples like 5, 6, 7, 8 samples. If your switching frequency is 10 kilohertz, in that case, the sample time is 1/2 into 10,000. So sample time will be very, very small. उसका मतलब sample time is very, very small means अगर आप फिर से sector 1 लेंगे, this is V1, this is V2, this is circular path, पहला sample अगर यहाँ है, sample time is very, very small. दूसरा sample बहुत close होगा इसके, very close, third sample, fourth sample. So you will get very large number of samples in one sector, and then in one cycle you will get hundreds and hundreds of samples. And that will have a good effect on the waveform. So therefore your voltage waveform will be almost sinusoidal because sample time is very, very small. So therefore it has been seen that in induction motor drives, the sample time is generally very, very small because switching frequencies, it may be 5 kilohertz, maybe 10 kilohertz, it may be 20 kilohertz, or it may be more than 20 kilohertz. Higher the switching frequency, smaller is the sample time. Smaller the sample time, larger will be the number of samples. और आपका reference vector steps में नहीं move करेगा, it will smoothly move like this. Sample time is very, very small. You will get huge number of samples in each sector, and in one cycle you will get hundreds and hundreds of samples, and that will give almost sinusoidal waveform of the voltage. Okay. Now let us try to see switching states in sector 1. Switching states in sector 1. I will again draw the sector 1. This is V1 equal to VDC, और यहाँ switching state है plus minus minus, और ये मेरा voltage space vector है V2 equal to VDC, and here switching state is plus plus minus, and I have zero voltage vector V0, which is minus minus minus, and another zero voltage vector V7, which is plus plus plus. And my reference vector, say this is my reference, rotating reference vector. At any instant of time, it's at an angle of alpha. How do I produce this rotating reference vector? By applying voltage space vector V1 for time interval T1, by applying voltage space vector V2 for time interval T2, and by applying voltage space vector Vz for time interval Tz. Okay? And then repeating it till the sector 1 is complete और आपका reference पूरा ये circulate हो जाता है. It completes its path, moves. Then it moves from sector 1 to sector 2, and then it repeats in other sectors. So therefore, I can start with zero voltage vector. I can apply minus 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 switching state. That means I apply zero voltage vector for time interval Tz by 2. My total zero voltage vector is Tz. I divide it into Tz by 2. And for Tz by 2, I apply minus 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 zero voltage vector. For another Tz by 2, I apply plus 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 zero voltage vector. I tell you why so my total Tz is equal to Tz by 2 plus Tz by 2. I will tell you why both the zero voltage vectors are applied. Okay, so I start with zero voltage vector. This zero voltage vector is applied across the load for time interval Tz by 2. Then I apply V1 voltage vector, which represents the switching state plus minus minus for time interval T1. Then I apply voltage space vector V2, which represents the switching state plus 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 minus for time interval T2. And then we apply another zero voltage vector V7, whose switching state is plus 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 for another Tz by 2. Now you must understand this. I could have applied minus 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 or plus 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 for entire time period Tz. Why I have divided this Tz zero time period into two equal intervals Tz by 2 and Tz by 2? The answer to this question is that if you apply only one zero voltage vector, say either minus 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 or plus plus plus, say for example you apply only minus 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 zero voltage vector. Minus 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 zero voltage vector means only the bottom switches are on. So that will cause unequal loading of the devices, because you are putting bottom devices on for some period, top devices you are not putting on. If you apply plus 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 zero voltage vector or zero switching state for entire zero time period Tz, then only top switches will be on, bottom switches will not be on. So in order to equally put on top devices and bottom devices, what we do, for half of the zero time period bottom devices are put on, and for other half of the time period top devices are put on. So that is why Tz is divided into two Tz by 2 periods. In first Tz by 2 period, the switching state is minus minus minus. That means zero voltage vector V0 is applied across the load with bottom switches on. And for another Tz by 2 interval, the switching state is plus plus plus. That means top devices are only on and voltage zero voltage vector V7 is applied. ये तो हो गया एक सब साइकिल में Ts. आपका कैरियर अगर आप ट्रायंगल के साथ ट्रायंगल कंपैरिजन के साथ कंपेयर करेंगे, योर कैरियर इज Ts एंड Ts सब साइकिल. तो हाफ कैरियर इज Ts, अनदर हाफ कैरियर इज Ts. तो ये तो हो गया एक सब साइकिल. तो दूसरा सब साइकिल फॉलो करेगा अनदर Ts. उसमें you first apply this plus 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 for Tz by 2. Then you apply plus plus minus for T2 time interval. Then you apply plus minus minus for T1 interval, and then you apply minus 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 for Tz by 2 interval. ये दूसरा सब साइकिल कंप्लीट करता है, and this completes your switching sequence. So therefore switching sequence should be like this. First of all, you apply switching state minus minus minus. Minus 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 means you apply voltage space vector V0. For how much time? For time interval tz by 2. Then you apply voltage space vector V1 for time interval T1. Okay, voltage space vector V1 represents the switching state plus minus. I have मैंने ऊपर लिखा है. Then you apply voltage space vector V2 for time interval T2, which represents the switching state plus plus minus. Then you apply zero voltage space vector V7 for time interval Tz by 2. Okay, तो ये मेरा एक सब साइकिल कंप्लीट हुआ. उसके बाद दूसरा सब साइकिल मेरा यहाँ से शुरू हुआ. तो you start with V7, you apply it for Tz by 2, followed by V2, apply it for T1 by 2, followed by V1, apply it for V2 is applied for T2, V1 is applied for T1, and followed by V0 again, which is applied for Tz by 2. So ये switching sequence है. This is how time averaging is done. ये TS subcycle है, this is another TS subcycle. Okay, this V0 zero voltage vector is applied for time period Tz by 2. V1 is applied for time period T1, V2 is applied for time period T2, V7 zero voltage vector is applied for time period Tz by 2. So that Tz by 2 plus Tz by 2 is Tz. Then this is completion of one sub cycle. Another sub cycle is equivalent to another carrier half period. You apply V7. अब आप reverse जाइए. V7. Apply it for Tz by 2 time interval. V2 apply for T2 time interval. V1 apply for T1 time interval. And V0 you apply for another Tz by 2 interval. So that Tz by 2 plus Tz by 2 is Tz. So this is the switching sequence. This is how you have to do in sector 1, and same you have to follow in other sectors. So let me show it with the help of diagram. Switching state is like this. First of all, see, this is my switching state. V0 followed by V1 followed by V2 followed by V7, then V7 followed by V2 followed by V1 followed by V0. ये एक सब साइकिल है TS, and this is another sub cycle TS. Let us see how we do it. V0 represents minus 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 switching state, followed by V1, V1 is plus minus minus, followed by V2, V2 is plus plus minus, followed by arrow, followed by V7, V7 is plus plus plus. ये एक सब साइकिल है. दूसरे सब साइकिल में फिर से V7, that is plus plus plus, followed by V2, which is plus plus minus, followed by V1, which is plus minus minus switching state, followed by V0, which is minus minus minus. ये एक सब साइकिल है. Let us show this state here. First, minus minus, zero voltage vector, minus minus minus, right? उसके बाद उसके बाद प्लस माइनस माइनस, उसके बाद प्लस माइनस माइनस, plus minus minus, voltage vector V1 for time interval T1. Okay, this is for, यहाँ पे लिखूंगा, this is for time interval Tz by 2. This voltage vector is for time interval T1. उसके बाद plus plus minus, उसके बाद plus plus minus, this is for time interval T2, right? उसके बाद plus plus plus, zero voltage vector, plus plus plus. Okay, this is also for time interval Tz by 2. तो ये मेरा सब साइकिल कंप्लीट हो जाता है. सब साइकिल TS कंप्लीट हो जाता है. Now another sub cycle will start. वो उल्टा start है. वो that will start with plus plus plus. So that will start with plus plus plus, then plus plus minus, then plus minus minus, and then minus minus minus. So this is for Tz by 2, T2 time interval, T1 time interval, and Tz by 2 interval. ये सब साइकिल दूसरा सब साइकिल है. So this is the switching state. Okay. Now let us draw the pole voltages. VR naught. During this first period, when zero voltage vector V naught is applied across the load, so this is voltage vector V naught, zero voltage vector, this is V1, this is V2, this is V7, this is V7, this is V2, this is V1, this is V naught. R phase has, minus. It's minus means its bottom device is on. So what will be pole voltage? Pole voltage will be minus VDC by 2. I will write here minus VDC by 2 will be the pole voltage, right? Then for time period T1, switching voltage space vector V1 is applied across the load, and switching state is plus minus minus. Plus minus minus means, top switch of R phase is on, and that makes pole voltage VRO plus VDC by 2. तो ये minus VDC by 2 से plus VDC by 2 jump करेगी. And then in next time interval, when voltage space vector V2 is applied, again it's plus, then again plus, plus, plus up to this. So that means यहाँ से यहाँ तक your phase leg or top switch remains continuously on, and your pole voltage VRO is plus VDC by 2 all throughout. उसके बाद ये minus हो जाता है, that means pole voltage becomes minus VDC by 2 again. So this is pole voltage VRO. What about V by O? V by O. You can see this is Y, this is R, Y, B. Y is minus, this bottom switch of phase leg Y is on. So pole voltage V by O is minus VDC by 2. Then it is minus here also, in next time interval also. So it remains minus VDC by 2. Then it is plus, 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 plus. For 4 intervals, it's positive. Plus means top switch is on and your pole voltage is plus VDC by 2. Then it is minus VDC by 2 again. So this is pole voltage V by O. Similarly, we can draw pole voltage VBO. Okay. B, it's minus, minus, minus. For 3 time intervals, it is minus, minus, minus. Minus, minus, minus means, the bottom switch of phase leg B is on. So your pole voltage VBO is minus VDC by 2, minus VDC by 2, minus VDC by 2 for 3 intervals. It's minus VDC. For 2 intervals, it's plus, plus means plus VDC by 2. And then it is minus VDC by 2 again. So these are my pole voltages, VRO, VYO, VBO. From these pole voltages, I can get one of the line voltage, say VRY. Let me show you one of the line voltages, say VRY. Now what is line voltage VRY? That is pole voltage VRO minus pole voltage VYO. In first first time interval, when voltage space vector V0 is applied across the load, VRO is minus VDC by 2, VYO is also minus VDC by 2. So minus VDC by 2 plus VDC by 2 is 0. So my line voltage is 0 during this time period. In next interval, VRO is when voltage space vector V1 is applied across the load. VRO is plus VDC by 2, VYO is minus VDC by 2. So plus VDC by 2 plus VDC by 2 is plus VDC. That means voltage pulse VDC will get applied across the load. Then from this interval to this interval, see VRO is VDC by 2, VYO is also VDC by 2. So they cancel, they subtract to 0. VDC by 2 minus VDC by 2 is 0 till this interval. 0. और फिर यहाँ से यहाँ तक, when voltage space vector V1 is again applied across the load, so your VRY is VRO minus VYO, so it's VDC by 2 plus VDC by 2, that's VDC. उसका मतलब ये हुआ that in one sub cycle, ये मेरा एक sub cycle यहाँ पे खत्म होता है. This is sub cycle TS. This is another sub cycle TS. In one sub cycle, the load will experience one voltage pulse, VDC, line voltage pulse across the load. And in 2 sub cycles, 2 voltage pulses 2 line voltage pulses will appear across the load. ये होता है एक मतलब कैरियर साइकिल में, अगर आप इसको कंपेयर करेंगे ट्रायंगल कंपैरिजन में. सो इन वन कैरियर, वन सब साइकिल, one positive voltage, line voltage will get applied across the load. In another sub cycle, another half carrier period, you have seen in triangle comparison also, in one carrier period, one positive voltage pulse will get applied across the load, VDC pulse. In another half carrier period, VDC will again get applied across the load. In space, in terms of space vector terminology, we don't call it carrier, half carrier period, we call it sub cycle. In one sub cycle, one positive voltage DC voltage VDC voltage pulse will get applied across the load. In another sub cycle, which is equivalent to another half carrier period for triangle comparison, another voltage pulse VDC will get applied across the load. That means in one carrier period or in 2 sub cycles here, 2 line voltage pulses get applied across the load. So this is the comparison between the two in triangle comparison method as well as in space vector based PWM. It remains same. In triangle comparison method, in one carrier cycle, 2 line voltage pulses are applied across the load. Same is the case with space vector PWM. In 2 sub cycles, 2 voltage line voltage pulses VRY, similarly VYB and VBR will get applied across the load. Right? This is switching sequence. Let us try to now derive the switching or gating pulses. Gating pulses for 6 switches of inverter. We will sketch the gating pulses in each sector. We'll start with sector 1. Okay, sector 1 is this. In sector 1, we apply 0 voltage pulse V0, 0 voltage space vector V0, which is minus 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 for time interval TZ by 2, and then V7, which is plus plus plus, which is also 0 voltage vector later on for another TZ by 2 in a subcycle. And then we apply voltage space vector V1, which is plus minus minus for time interval T1. And we apply voltage space vector V2, which is plus plus minus for time interval T2. Okay, and that gives us reference vector Vref. So switching sequences like this, I'll again reproduce that minus minus minus. V0, 0 voltage vector is applied for time interval TZ by 0, TZ by 2. Then voltage space vector V1 is applied for time interval T1, so plus minus minus. Then voltage space vector V2 is applied for time interval T2, plus plus minus is switching state. Then voltage space vector, 0 voltage space vector V7 is applied for another TZ by 2, so plus plus plus. This is one switching, one subcycle. In another subcycle, just opposite of this, plus plus plus, plus plus minus, plus minus minus, minus minus minus. So therefore, I have 6 switches of the inverter. This is switch S1. Let me first of all take top switches, S3, S5, and bottom switches are S4, S6, and S2. They are complementary. For example, in phase leg A, the 2 switches are like this. This is S1, this is S4. When S1 is on, S4 should be off at that time. When S4 is on, S1 should be off at that time. They are complementary. Both should not be on simultaneously, because that will, cause dead short circuit of DC source if both are simultaneously on. Okay. So they are complementary. If you know the switching pulse pattern of S1, so switching pulse pattern of S4 will be just complementary, opposite of that of S1. Okay. So minus minus, so I will take time interval TZ by 2. Yeah, let me call this time interval T0, then time interval T1, T2, T7, then again T7, T2, T1, T0, right? Let us take phase leg R. Phase leg R in time interval T0, minus minus minus, zero voltage vector is applied across the load. So phase leg R's, this is phase leg R, its bottom switch is on. Bottom switch is on means S4 is on. So S1 is off at that time. ये S1 मुझे KI, मेरा S1 है. S1 is off. This is T0. Let me show these time intervals here. T1, T2, T7, and again T7, T2, T1, T0. So bottom switch is on, so S1 is off. Then top switch is on because it is plus 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 plus. 6 intervals के लिए ये plus plus है. Plus 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 plus. So that means the control pulse to switch S1 should be on for 6 time intervals. T1, T2 may be on a top switch, so S1 should be gated, its control pulse should be high. Then it's again plus, that means top switch is again on, you have to apply, then again for next. So this is the control pulse pattern for, your switch S1. What about S3? S3 belongs to middle leg. ये middle leg है. This is S3. This is S6. This is phase leg Y. Middle leg में again it's off. I mean its bottom switch is on for first 2 intervals for T0 and T1, and then for 1, 2, 3, 4 and 1, 2, 3 and 4 intervals. Middle switch, this top switch of middle leg is on. 4 intervals के लिए on है. So that means 1, 2, 3, 1, 2, 3, 4. यहाँ से यहाँ तक इसकी control pulse high होनी चाहिए. It should be high. So this is the switching pulse pattern for S3. What about S5? S5 belongs to the third arm or third leg of the inverter. This is S5 and this is S2. S5 आप देख सकते हैं, it belongs to phase leg B. Phase leg B का bottom switch 1, 2, 3 intervals के लिए on है, और top switch S5 is on for only 2 switching intervals, 1 and 2. Okay. 1 and 2 means this is T0, T1, T2, T7 and T7. T7 and T7. So ये T7 interval है और ये next. So it is high for only these 2 intervals. So this is switching pulse pattern for S5. So you have to understand it. And then what about S4? S4 is the complementary switch of S1. Whenever S1 is on, S4 will be off. And whenever S1 is off, S4 will be on. So इसका pulse pattern हम आराम से निकाल सकते हैं from this. In first time interval T0, S1 is off, so S4 will be on during this period. And in time interval from here to here, S1 is on, so S4 will be off. Then in this last time interval, S1 is on, S1 is off, so S4 will be on. So ये S4 का time interval. So you can very clearly see in time interval T0, switching this voltage space vector V0 is applied across the load, which represents the switching state minus minus minus. Minus means phase leg R का bottom switch on है. You can clearly see bottom switch will be on only when you issue control pulse to it. So you are issuing control pulse to it. Bottom switch is on. That gives minus status. Then for voltage space vector V1 is applied, V2 is applied, then V7 is applied, then again V7, V2, V1. During all these intervals, top switch is on, and top switch is on means the voltage top switch is on, you can see top switch is on throughout. So the control pulse to top switch S1 is continuously on, and then again last zero voltage vector bottom switch is on. Okay, this is about S1 and S4. S3 का complementary क्या है? S6, ये S3 है और S6 ये है. इसका when S3 is off, S6 will be on. When S3 is on, S6 will be off. ये इसका complementary. What about complementary of S5? S5 का complementary switch क्या है? S2. When S5 is off, S2 will be on. तो इसका control pulse pattern है. And when S5 is on, S2 will be off. So this is the gating pulse pattern. You have to generate the gating pulse in this way in sector 1. अच्छा, उसके बाद ये टाइम इंटरवल सेम नहीं रहता सेक्टर 1 में. एज योर रेफरेंस वेक्टर मूव्स फ्रॉम V1 to V2, T1 will decrease, T2 will increase. तो ये कंट्रोल पल्सेस की विड्थ किसी की कम हो जाएगी, किसी की ज्यादा हो जाएगी. एज you रेफरेंस वेक्टर rotates in sector 1 from V1 to V2. This is the control pulse pattern or gating pulse pattern in sector 1. Let us quickly draw it for sector 2. Gating pulse pattern for sector 2. For sector 2, this is my sector 2. It's my voltage space vector V2, which is plus plus minus, and voltage space vector V3, which is minus plus minus. It's applied across the load. Or mera reference vector somewhere. This is my reference vector. Okay, so rotating reference vector. Right. So what is the sequence? Sequences, first you apply voltage space vector V0 for time interval tz by 2 या t0 उसको कहिए. Then you apply voltage space vector V3. Okay, you apply we are considering sector 2. You apply voltage space vector V3. Then you apply voltage space vector V2 for time interval T2. Then you apply voltage space vector V7 for, this is for time interval T1, this is time interval T2, this is for time interval T7. T0 and T7 are Tz by 2 each. This completes one subcycle. Then another subcycle will be just opposite. V7, V2, V3 and V0. This is for T7, this is T2, this is T1, this is T0. Okay, V0 means switching state minus minus minus. V3 means V3 की switching state क्या है? Minus plus minus. V2 की switching state है plus plus minus, and V7 is plus plus plus. Okay, then again V7 plus plus plus, then T2 plus plus minus, then T1 minus plus minus, and then T0 minus minus minus. ये complete करता है 2 subcycles. Let us see the switching pulse pattern. S1, S3, S5, S4, S6, S2. In first time interval T0, R phase has a switching state of minus. इसका मतलब इसका bottom switch on है. So you don't have to apply control pulse. ये मैं पहले ये 1, 2, 3, 4, 5, 6, 7, 8. ये 8 time interval है total. 1, 2, 3, 4, 5, 6, 7, 8. In first time interval T0, R phase का switching state है minus. That means its bottom switch is on. So S1 will be off. In second time interval T1, when V3 voltage vector space vector is applied across the load, it's again minus. Then during time T1 में भी ये minus है. Then during time interval T2, it's plus. ये देखिए ये plus है. Plus means stop switch is on. So S1 को on करना है. T2 में S1 को on करना है. तो ये ऑन हो जाएगा. Then T7 time interval में when zero voltage space vector V7 is applied, it's again plus. तो ये ऑन ही रहेगा. उसके बाद T7 फिर से आएगा. You can see T7 फिर से आता है. It is plus, ऑन ही रहेगा. उसके बाद T2 फिर से आता है. प्लस ऑन ही रहेगा। उसके बाद दिस इज T7 T2, उसके बाद T1 और T0 फिर से आएंगे तो ये लो हो जाएगा। सो दिस इज कंट्रोल पल्स पैटर्न फॉर स्विच S1। व्हाट अबाउट S3? S3 माइनस है, फिर प्लस 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 ऑल थ्राउट है। का मतलब ये S3 is off in first time interval T0 and then it is on throughout. This is S3. What about S5? S5 is minus minus minus. तो 3 इंटरवल्स में माइनस मीन्स इसका टॉप स्विच ऑफ है, और 2 इंटरवल्स में यू कैन सी प्लस प्लस इट इज ऑन फॉर 2 इंटरवल्स। ये 2 इंटरवल्स है, इन 2 इंटरवल्स में इसकी कंट्रोल पल्स हाई रहेगी। So this is the switching pulse pattern for S5. Once you know the switching pulse pattern for S1, S3, S5, you can derive the switching pulse pattern for bottom switches S4, S6 and S2, which are complementary to top switches. S4 is complementary switch of S1. So whenever S1 is off, S4 will be on. Its control pulse will be high. And whenever S1 is on, S4 will be off. Its control pulse is low. Then again, S6 is complementary of S3. ये ऑफ है पहले इंटरवल में, तो ये हाई होगा। ये हाई है यहाँ से यहाँ तक, तो ये लो होगा, इसकी कंट्रोल पल्स लो रहेगी, and then it will be high in last interval. S2 is complementary of S5. S5 is high during this interval, इसकी कंट्रोल पल्स हाई है, तो इस इंटरवल में इसकी लो रहेगी, बाकी पूरे इंटरवल में S2 हाई रहेगा। सो दिस इज द कंट्रोल पल्स पैटर्न। ये 2 इंटरवल्स हैं, सॉरी ये 2 इंटरवल्स हैं, दीज आर 2 इंटरवल्स। ये सो दिस इज द कंट्रोल पल्स पैटर्न फॉर ऑल द 6 switches of inverter in sector 2. So in a similar way you can draw the switching pulse pattern for all the 6 switches of the inverter in other sectors. बाकी sectors में भी आपको इसी तरह ये switching sequence, you have to draw this switching sequence, and once you draw the switching sequence, then as per this switching sequence you can draw the control pulse pattern for all the 3 switches. I leave that to you as an exercise. Please try to do it yourself. Try to draw control pulse pattern for all the 6 switches of the inverter in all the 6 sectors. First 2 sectors I have already drawn, and same way you can draw for in other sectors. With this I will end my today's lecture. So in today's lecture, summarizing, we have tried to develop the concept of how voltage space vectors, 6 voltage space vectors and 2 zero voltage space vectors can be used for generating a rotating reference voltage vector or rotating reference vector, which will generate or which will represent 3-phase sinusoidal voltages. Okay, in all the 6 sectors we have seen how we can use the adjacent voltage space vectors and generate the rotating reference vector, and hence this rotating reference vector is basically representative of 3-phase inverter sinusoidal output voltages. And we also try to draw the control pulse pattern for switches for those of you who want to implement this space vector PWM for a 2-level 3-phase voltage source inverter. This control pulse pattern will help them in designing the simulation model. Okay, so more on it in next lecture. Thank you.